Welcome back. In this video we will look at truth tables, and truth tables are essentially a symbolic way of determining whether or not statements are true or false. So to begin with, when we're talking about statements that are true or false, the word here that we'll use is proposition. Whenever you see a proposition, what it means is that it's making an assertion or a denial. So some quick examples. A proposition could be something like 2 plus 3 is equal to 5. This is an assertion. It is saying that that when you add these two numbers, it is equal to 5. Or, for instance, a proposition could be written out in words. It could be, it is raining. Both of these are assertions. If I wanted to make a denial, I could say it is not raining. And this would be a denial. This is saying that something is not true. We have to be a little bit careful because, for instance, right here, if I said 17 times 18, I'm not really making an assertion. I'm just saying take these two numbers and multiply them together. I'm not making a denial. This is not a proposition. Neither is say something like cold water, or if I just wrote something like running. I'm not saying anything, really. I'm not making a statement that you could refute or prove. A proposition will always either be true or false. So 2 plus 3 is equal to 5 could be a true statement. It could be a false statement. Hopefully you recognize that this is true. It is not raining. Well, this depends. You'd have to look outside and see. Is it raining or is it not raining? But we could determine if it is true or false. 17 times 18 isn't true or false. It's just a number. And we are able to make sentences that are neither true or false, but these won't be propositions either. Normally these would involve paradoxes, like if I said, this sentence is false. If it was false, then it'd be true, but if it was true, then it'd be false. It's not a proposition, so we won't really consider things like this. So let's look at truth tables. And to begin with, let's look at the logical words and or. So if I start with two propositions, maybe P is 2 plus 3 is equal to 5, and Q is it is not raining. These could be two propositions, just any two propositions that we want. If I separate two propositions with an and, in order for this entire this proposition here, the combination of P and Q, in order for that whole thing to be true, and means that both P and Q are true. Both P is true and Q is true. And this makes sense in everyday language. If I said 2 plus 3 is equal to 5 and it is not raining, that means that 2 plus 3 is equal to 5 on one hand, but on the other hand, it would mean that it is not raining. So both things would be true. So and is pretty easy to deal with. In order for two propositions separated by an and to be true, both the propositions have to be true individually. Or is a little bit different. If I said P or Q is true, it could be that P is true but Q isn't. Or it could be that Q is true and P isn't. And there's even one more possibility, that they're both true. I think the best way to phrase P or Q would be the following. At least one of P or Q is true. And this is where things get a little bit tricky. I use the word or in my definition, but hopefully we can see what's going on. And requires both things to be true, or is just at least one of them. So let's put this into a table. So if we have P and Q, these are propositions. They can be either true or false in any sort of combination. It could be that P is true and Q is true. It could be that they're both false. Or it could be that one is true and one is false, or vice versa. So we have all sorts of different combinations of true and false here. So when we look at P and Q, here we see that, well, in order for P and Q to be true, both P has to be true and Q has to be true, which is this row right here. But when we look at any of the other three rows, we see that, oh, in the second row, Q is false. So P and Q is false because it needs both of them to be true. In the third row, P is false. So P and Q, well, that's also false because, well, one of them is false. And the final row, it's definitely false because both P and Q were false. So when we're looking at AND, the only way for an AND statement to be true is if both of them were true to begin with. When we move on and we look at OR statements, if we look at P or Q, again, at least one of P or Q is true. Well, in the first row, at least one of them is true. In the second row, at least one of them is true. In the third row, at least one of them is true. So P or Q is going to be true a lot more often. And in that last row, if both of them are false, well, P or Q is also false because we didn't have any true statements in there. Okay, so AND and OR is pretty straightforward. You need both of them to be true for an AND statement, or you need at least one of them to be true for an OR statement. And we're good to go. One other type of statement is going to be implications. And in an implications, we have if P, then Q. Another way to phrase this is whenever P is true, then Q is true. So the time that we would use implications would be when knowledge of something implies knowledge of something else. And I think the best, one of the simplest statements that we can make that's an implication is the following. If it is raining, then it is cloudy. And this is generally true. If it's raining on you and you look up, you're probably going to see clouds. So in general, we would think of this as a true statement. And the fact that it is raining gives us some information about the next part. So if it is raining, then it is cloudy. We can separate this into parts. So we can see here we have a proposition. This is also called the hypothesis. This is a slightly different use of the word than in other contexts, but the hypothesis is the information that we would check before looking at the second proposition, which is called the conclusion. So this is another proposition, and in particular, this is called the conclusion, like I just said. So using information about the hypothesis gives us some information about the conclusion. So when we want to see if an implication is true or false, we need to see, okay, so we have all of our combinations. It could be that the first proposition, the hypothesis, so again, I'll indicate this, the hypothesis and the conclusion. It could be that the hypothesis is true, the conclusion is false. The hypothesis is false, conclusion is true, or they could both be false. And this is maybe a little bit trickier to see. But the one thing that I want to ask is, when would if P then Q be false? So the question is it false there? Could it be false here? And in my opinion, the easiest way to see this is, what would it take? Erase some of these lines. What would it take to prove this false? If I wanted to say, if it's raining, whenever it's raining, it's always cloudy. What would it take to prove me wrong? Well, if you could ever go out and find a day where it was raining, but it wasn't cloudy, I would be wrong. So what did it take to prove me wrong? The hypothesis had to be true. We had to find a day that it was raining, but we needed to say, but it isn't cloudy, so your implications is wrong. So if we ever found a day when the hypothesis was true, but the conclusion was false, our implications is wrong. And the rest of these are maybe a little bit trickier to fill out. In this first line, whenever we have the hypothesis true and the conclusion is also true, this makes this implication a true statement. It might not be very meaningful. I could say something like, if 1 plus 1 is equal to 2, let me reword this. If it is Tuesday, then 1 plus 1 is equal to 2. This doesn't really mean anything, because if you were to look at this on a Tuesday, the hypothesis would be true and the conclusion would be true, so the implications is true. But the day of the week doesn't change what numbers are equal to which other numbers. So this doesn't really have much use. It doesn't have much meaning. But on Tuesdays, this is true. Well, what about on Wednesday? Well, we come to this on Wednesday and we see that the hypothesis is false. So the question is, if the hypothesis is false, what about the whole thing? Is this a true statement? Is it a false statement? And it turns out that these are true. And I think the best way to understand why these are also true is, if the hypothesis is false, then we have no information. If it's not Tuesday, we don't have information about our conclusion. Down here, if it's raining, then it's cloudy. If you go out and it's not raining, well, this statement doesn't say it should be cloudy or should not be cloudy. This statement doesn't say anything. This statement only gives information when it is raining. So if we have no information, we can't prove it false, so it must be true. This is not the best sort of logic to get into political or religious discussions about, but in a very rigorous mathematical sense, if you can't prove a statement false, it has to be true. So here, whenever the hypothesis is false, the implications is simply going to be true, and it's called a vacuously true statement. Vacuous meaning it's kind of empty. It doesn't mean anything. If it's not Tuesday, this doesn't give us any information. If it's not raining, this doesn't give us information. So it's a vacuous statement. And the very last thing to mention is just the word not. So whenever you have a statement, whenever you have a proposition, say like 1 plus 1 is equal to 2, I can just write these down, 1 plus 1 is equal to 2, you can add a negation in here. So if I wanted to say, let's just say, not this statement, what would that really mean? That would be that 1 plus 1 is not equal to 2. Or I could say it is Tuesday. If I were to negate the statement, it would be it is not Tuesday. Okay? So whenever you have a statement, you can negate it using the word not. And if the negation of a statement is true, that's the same thing as just saying that the original statement is false. Okay? So it's either Tuesday or it is not Tuesday. So if it's Tuesday, then the first statement is true and the second statement is decidedly false. If it's not Tuesday, then the first statement is false and the second statement is true. So when you have a proposition, either it is true or its negation is true. One or the other must be true. And the truth table for this is pretty simple. We only have one proposition here, so it's either true or false. And when we negate it, well, if it was true to begin with, it becomes false. And if it was false, it becomes true.